Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss how reboilers work, and we will also discuss thermosiphon, gravity, feed, and forced concepts in reboilers. We will discuss 4 types of reboilers in this video. Once through thermosiphon reboilers. Circulating thermosiphon reboilers. Forced circulation reboilers. Kettle or gravity-fed reboilers. There are dozens of other types of reboilers, but these 4 represent the majority of applications. Regardless of the type of reboiler used, the following statement is correct. Almost as many towers flood because of reboiler problems as because of tray problems. The theory of thermosiphon, or natural circulation, can be illustrated by the airlift pump shown in picture. This system is being used to recover gold-bearing gravel from the river in Africa. Compressed air is forced to the bottom of the river through the airline. The air is injected into the bottom of the riser tube. The aerated water in the riser tube is less dense than the water in the river. This creates a pressure imbalance between points A and B. Since the pressure at point B is less than that at point A, water as well as the gold and gravel is sucked off the bottom of the river and up into the riser tube. We can calculate the pressure difference between points A and B as follows. HRW, DRW, minus HRT, DRT, divided by 2.31 equals delta P, where HRW equals height of water above the bottom of the riser in feet. DRW equals specific gravity of fluid in the riser, in this case 1.0. HRT equals height of the aerated water in the riser tube in feet. DRT equals specific gravity of aerated water in the riser tube. This number can be obtained only by a trial and error calculation procedure. dP equals differential pressure between points A and B in psi. In a thermosiphon or natural circulation reboiler, there is, of course, no source of air. The aerated liquid is a froth or foam produced by the vaporization of the reboiler feed. Without a source of heat, there can be no vaporization. And without vaporization, there will be no circulation. So, we can say that the source of energy that drives the circulation in a thermosiphon reboiler is the heating medium to the reboiler. Thermosiphon reboilers. Once-through thermosiphon reboilers. This picture shows a once-through thermosiphon reboiler. The driving force to promote flow through this reboiler is the density difference between the reboiler feed line and the froth-filled reboiler return line. For example, the specific gravity of the liquid in the reboiler feed line is 0.600. The height of liquid above the reboiler inlet is 20 feet. The mixed phase specific gravity of the froth leaving the reboiler is 0.061. The height of the return line is 15 feet. Feet of water per psi equals 2.31. The differential pressure driving force is then 20 feet times 0.600 minus 15 feet times 0.061, divided by 2.31 equals 4.7 psi. What happens to this differential pressure of 4.7 psi? It is consumed in overcoming the frictional losses due to the flow in the reboiler. Inlet line. Outlet line. Nozzles. If these frictional losses are less than the 4.7 psi we have calculated above, then the inlet line does not run liquid full. If the frictional losses are more than the 4.7 psi, the reboiler draw-off pan overflows, and flow to the reboiler is reduced until such time as the frictional losses drop to the available thermosiphon driving force. The once-through thermosiphon reboiler, shown in picture, operates as follows. All the liquid from the bottom tray flows to the reboiler. None of the liquid from the bottom of the tower flows to the reboiler. All the bottom's product comes from the liquid portion of the reboiler effluent. None of the liquid from the bottom tray flows to the bottom of the tower. This means that when the once-through thermosiphon reboiler is working correctly, the reboiler outlet temperature and the tower bottom temperature are identical. If the tower bottom temperature is cooler than the reboiler outlet temperature, something has gone wrong with the thermosiphon circulation. Loss of once-through thermosiphon circulation. There are several common causes of loss of circulation. The common symptoms of this problem are inability to achieve normal reboiler duty, low reflux drum level, accompanied by low tower pressure, even at a low reflux rate, bottoms product too light, reboiler outlet temperature hotter than the tower bottom temperature. Opening the steam or hot oil inlet heat supply valve does not seem to get more heat into the tower. The typical causes of this problem are bottom tray and tower leaking due to a low dry tray pressure drop. Bottom tray, seal pan, or draw-off pan is damaged. Reboiler is partially plugged. Reboiler feed line is restricted. Reboiler design pressure drop is excessive. Tower bottom liquid level is covering the reboiler vapor return nozzle. If the loss of circulation is due to damage or leakage inside the tower, one can restore flow by opening the startup line valve as shown in this picture and raising the liquid level. But if the reboiler is fouled, this will not help. This picture shows a once-through thermosiphon reboiler with a vertical baffle. This looks quite a bit different from previous, but process-wise, it is the same. Note that the reboiler return liquid flows only to the hot side of the tower bottoms. Putting the reboiler return liquid to the colder side of the tower bottoms represents poor design practice. While most designers do it this way, it is still wrong. Circulating thermosiphon reboilers. My last statement requires some clarification. But to understand my explanation, an understanding of the important differences between a once-through thermosiphon reboiler and a circulating thermosiphon reboiler is critical. This picture shows a circulating reboiler. In this reboiler, the reboiler outlet temperature is always higher than the tower bottom temperature. Some of the liquid from the reboiler outlet will always recirculate back into the reboiler feed. Some of the liquid from the bottom tray drops into the bottom's product. The tower bottom product temperature and composition are the same as the temperature and composition of the feed to the reboiler. The liquid feed rate to the once-through thermosiphon reboiler is limited to the amount of liquid overflowing the bottom tray. The liquid feed rate to the circulating thermosiphon reboiler can be quite high, limited only by the available liquid head thermosiphon driving force. However, we should note that the liquid head thermosiphon driving force for a circulating thermosiphon reboiler is proportional to the height of the liquid level in the bottom of the tower above the reboiler inlet nozzle, whereas with a once-through thermosiphon reboiler, as described previously, the corresponding height is the elevation of the floor of the draw-off pan sump above the reboiler inlet nozzle. For a circulating thermosiphon reboiler, the rate of circulation can be increased by increasing the steam or hot oil flow through the reboiler. This reduces the specific gravity or density of the froth or foam in the reboiler effluent line, increasing the tower bottom's liquid level. However, should this level reach the reboiler return nozzle, thermosiphon flow will be restricted or even stop. Then the reboiler heat duty will be reduced, and the tower pressure will drop. Sometimes this may cause the tower to flood. Circulating versus once-through thermosiphon reboilers. I said before that it was wrong to return the effluent from a once-through reboiler with a vertical baffle to the cold side of the tower's bottom. Doing so would actually make the once-through thermosiphon reboiler work more like a circulating reboiler. But if this is bad, then the once-through reboiler must be better than the circulating reboiler. But why? The once-through reboiler functions as the bottom theoretical separation stage of the tower. The circulating reboiler does not, because a portion of its effluent back mixes to its feed inlet. This back mixing ruins the separation that can otherwise be achieved in reboilers. Regardless of the type of reboiler used, the tower bottom product temperature must be the same to meet product specifications. This is shown in this picture. However, the reboiler outlet temperature must always be higher in the circulating reboiler than in the once-through reboiler. This means that it is more difficult to transfer heat in the former than in the latter. Because the liquid from the bottom tray of a tower with a circulating thermosiphon reboiler is of a composition like that of the bottom's product, we can say that the circulating thermosiphon reboiler does not act as a theoretical separation stage. However, the liquid from the bottom tray of a tower with a once-through thermosiphon reboiler can be quite a bit lighter in composition and hence cooler than the bottom's product composition, and thus we say that the once-through thermosiphon reboiler does act as a theoretical separation stage. The cooler the liquid flow from the bottom tray of a tower, the less the vapor flow through that tray. This is because the hot vapor flowing up through a tray heats up the downflowing liquid. This means that there is a greater vapor flow through the bottom tray of a tower with a circulating thermosiphon reboiler than there would be through the bottom tray of a tower with a once-through thermosiphon reboiler. Everything else being equal, then, the tower served by the circulating reboiler is going to flood before the tower served by the once-through reboiler. The superfractionation stage. A once-through thermosiphon reboiler not only functions as the bottom theoretical stage of a tower, but it also functions as if it is a superfractionation stage. This means that it is more important than any individual tray in the tower. This is especially true with a multi-component tower bottoms product. We will discuss this concept of the superfractionation in an upcoming video. Excessive thermosiphon circulation. In a once-through reboiler, the liquid flow coming out of the reboiler is limited to the bottom's product. In a circulating reboiler, the liquid flow coming out of the reboiler can be extremely high. If the reboiler return nozzle is located too close to the bottom tray of the tower, the greater volume of liquid leaving the nozzle can splash against the bottom tray. This alone can cause the entire column to flood. The best way to stop this flooding is to lower the tower bottom level. Sometimes higher rates of thermosiphon circulation are good. They help prevent fouling and plugging of the reboiler due to low velocity and dirt in the bottom's product and especially high vaporization rates. If the percentage of vaporization in a once-through reboiler is above 60% and dirt in the bottom's product is expected, then a circulating reboiler would be the better choice. Forced circulation reboilers. The picture shows a once-through forced circulation reboiler. Such a reboiler differs from a thermosiphon reboiler in that it has a pump to force circulation, rather than relying on natural or thermosiphon circulation. This extra pump seems rather wasteful, and it is. The great advantage of forced circulation is that careful calculation of the pressure drops through the reboiler and associated piping is not critical. But as we can see in this picture, the operator now has two tower bottom levels to control. Further, if the hot side liquid level rises above the reboiler return nozzle, the force of the vapor and liquid rushing back into the column will cause the trays to flood, but the reboiler heat input will not be affected. Most often, forced circulation is used with fired reboilers. If flow is lost to such a reboiler, furnace tube damage is likely to result. Hopefully, this is less likely to occur with a forced circulation reboiler. Also, a higher pressure drop of a furnace may force the designer to use a pump. Sometimes we also see a forced circulation reboiler system if the reboiler heat is to be recovered from a number of dispersed heat sources that are far away from the tower and hence a lot of pressure drop has to be overcome. Kettle reboilers. Reboilers are sometimes inserted into the bottom of a tower. These are called stab-in reboilers. It is not a terribly good idea, because it makes it more difficult to fix a leaking or to clean a fouled reboiler without opening the tower itself. However, the Kettle reboiler, shown in this picture, has essentially the same process performance characteristics as the stab-in reboiler, but is entirely external to the tower. Note that in a Kettle reboiler, the bottom's product level control valve does not control the level in the tower, it controls the level on the product side of the reboiler only. The liquid level on the boiling or heat exchanger side of the kettle is controlled by the internal overflow baffle. But what controls the tower bottom liquid level? To answer this, let us see how such a gravity-fed or kettle reboiler works. 1. Liquid flows out of the tower into the bottom of the reboiler's shell. 2. The liquid is partially vaporized. 3. The domed top section of the reboiler separates the vapor and the liquid. 4. The vapor flows back to the tower through the riser line. This is the column stripping vapor or heat source. 5. The liquid overflows the baffle. The baffle is set high enough to keep the tube submerged. This liquid is the bottom's product. The liquid level in the bottom of the tower is the sum of the following factors: the nozzle exit loss of the liquid leaving the bottom of the tower, the liquid feedline pressure drop, the shell side exchanger pressure drop, which includes the effect of the baffle height, the vapor line riser pressure drop, including the vapor outlet nozzle loss. Note that it is the elevation, or the static head pressure, in the tower that drives the kettle reboiler. That is why we call it a gravity-fed reboiler. Also, the pressure in the kettle will always be higher than the pressure in the tower. This means that an increase in the reboiler heat duty results in an increase of liquid level in the bottom of the tower. Should the liquid level in the bottom of the tower rise to the reboiler vapor return nozzle, the tower will certainly flood, but the reboiler heat duty will continue. Unfortunately, reboiler shell side fouling may also lead to tray flooding. This happens because the fouling can cause a pressure drop buildup on the shell side of the reboiler. Remember, though, that the increased tower bottom liquid level will not be reflected on the indicated bottom level seen in the control room, which is actually the level at the end of the kettle reboiler. This is a constant source of confusion to many operators who have towers that flood because of high liquid levels, yet their indicated liquid level remains normal. Don't forget fouling. I have seen towers equipped with kettle reboilers flood due to high liquid levels a dozen times in my career. The story is always the same. The elevation difference between the reboiler vapor return nozzle and the overflow baffle inside the kettle is only 2 or 3 feet. The designer has forgotten about shell-side fouling. A reasonable allowance for shell-side fouling could be an extra 1 psi of dP. If we are dealing with a reboiler feed with a specific gravity of 0.65, then the required height of the liquid inside the tower would increase by about 3.5 feet. This would increase the height of the reboiler return nozzle also by 3.5 feet. Vapor binding in steam reboilers. The accumulation of non-condensable on the tube side of horizontal steam reboilers has an extremely detrimental effect on heat transfer. The origins of the non-condensable vapors are contamination of the steam supply with CO2, N2, or light hydrocarbons, reboiler tube leaks, air trapped inside the channel head on startup. There are several theories as to how these non-condensable reduce the reboiler duty to such a great extent. Tubes fill with gas and prevent the flow of steam into those tubes. The non-condensable produce a film of gas around the tubes. The non-condensable reduce the steam partial pressure and thus reduce the condensation temperature of the steam. Mostly loss in reboiler duty over 1 day is due to a tube leak, or the more gradual loss of reboiler duty over 1 month is due to CO2 accumulation in the channel head. Regardless, to alleviate the loss of reboiler duty, vent the channel head just below the bottom channel head past partition baffle. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.